Lab 3, Circuits by Shervin Praveen. The purpose of this lab is to measure the voltage and current of a circuit with different components. Models and fundamental principles. We will be using the node rule, the loop rule, and Ohm's law, and these are illustrated here. Experiment. Our experiment includes creating different circuits and testing the current and voltages throughout each circuit. The first circuit we create is shown on the left. We begin with two batteries in series, which add the electric potential voltage, which is connected to a wire and is led to an ammeter. Next are two resistors lined up also in series, which are then connected to another ammeter, which complete the circuit. We will also be using a voltmeter to measure the voltage differences between each parts. The two batteries are measured at 1.5 volts. The two resistors are at 47 and 100 ohms respectively, and the voltmeter is at 0.2 farads. Conservation. In the circuit shown, we predict the currents of both ammeters to be 0.02 amps by using Ohm's law. V equals I times R. Rearranged, this is I equals V divided by R, where R is the sum of resistors. We have I equals 3 divided by 147, which gives us our 0.02 amps. Our predictions were correct based on the circuit reading of the ammeter. Also, the ammeter is read the same, no matter the direction it faces. Voltage differences. The potential differences for each path are given below from the circuit. Following conventional current, the battery adds our voltages, and the resistors or loads subtract. The sum of our measured differences we expect to get is 0 volts from the loop rule, and that is what we get when we sum them up. Now we are asked to measure the voltage from the negative terminal of the battery to each point of the circuit. When we start from the negative terminal of the battery and get to the two batteries, that is where we get our 3 volts, and through each resistor our voltage goes back and back until we reach 0 volts, which is what we expect from the loop rule. Why doesn't the ammeter's reading change when you attach it to the voltmeter? Since the voltmeter's resistance is so high, the electrons travel through the resistor without traveling through the voltmeter, since that is the path of least resistance. Capacitor circuit, or RC circuit. With the capacitor circuit, the light bulb shines brightly until the capacitor becomes fully charged. Again, without a battery, the light bulb shines brightly until the potential difference in the capacitor reaches 0. Time dependence graph. Next, we plotted a graph for the capacitor discharge in respect to time with the load of a 30 ohm light bulb. We notice on the graph on the right, our slope is negative 0.167, and this is a linear slope. Comparing answers for RC. The RC with the graph. We use the slope we got from the previous function, which was negative 0.167, and with the formula RC equals negative 1 over the slope, we find our RC to be 5.988 seconds. And with the formula RC equals resistance times capacitance, plugging in we find that RC equals 30 times 0.2, and our answer also comes out to 6 seconds, which is very close. Questions. What if we use an actual ammeter instead of an ideal simulated ammeter? Our answer might be a very minuscule difference, because in the simulation they assume the ammeter has no resistance, but in real life when the electrons travel through there will be a little resistance. What if we did this experiment in real life with real batteries and capacitors and with no resistance? In this case, the capacitors would charge nearly instantly, but in the real world this would not be possible since the wires provide a little bit of resistance. Thank you.